Right. So today we have Kimyeong Lee, who will tell us about VOAs and CFTs on Magic Triangle. Take it away.
All right. So let me all right, so let me start. Okay, so this work I have done with Kaiwen Son of University of Science and Technology of China, and we hope to finish this work as soon as possible. We have draft almost done. So this work has been started like last October, and it's about some 2D conformal field theory related to magic triangle. Probably most of you never heard of magic triangle. Maybe you heard of magic square. So let me start with what now I'm trying to going to next page. Obviously. Okay. So this wrap up my outline of the talk. So I'll review 2D conformal field series first. Then I'll introduce magic square and magic triangle. And the magic triangle has been incomplete and will complete the magic triangle, whatever it means. And then we'll discover a few magic causes related to magic triangle. And we'll find 5 atomic theories of this related to 30 series of one magic triangle. And then we'll go to higher levels and so on, then conclude. So let's start this 2D conformal field series and their characters and equation satisfied by these characters, which is called modular linear differential equations. So among the 2D conformal field series, there are something called rational conformal field series. And in rational conformal field series, it has a finite number of chiral primary operators with a rational central charge being rational number, and also conformal weight being rational number. Now, the characters, which is torus partition function, we are looking just holomorphic part of Virasoro algebras or generalized chiral algebras. And for each primary operators, we have Hilbert space, and then we have this trace Q, which is 2 pi I tau times L0, which is Virasoro generator L0 minus C over 24. And that generates a weight zero vector valued modular form, which is called characters. So there are characters for each primary operators or for each conformal weights. Now, this characters satisfy modular linear differential equation, which was proposed by Eguchi and Ogri, and also became a major tool for classification of rational conformal field theory by Matsuo, Muki, and Sen. And this equation satisfies some linear equation, modular linear differential equation. And differentiation is called the Ramanujan-Serre derivative, which is covariant derivative of this differential form. And when you take a derivative, you increase the weight by 2, and this still vector modular forms. And the coefficient zeta k is weight 2k in modular forms, usually ratio of the Eisenstein series E4 and E6. Now, 2 character case, central charge, let's say C, and weight is, one has to always have a vacuum character, which has weight 0, and then another character or operate with weight H, and their characters Chi0 and Chi1, and there's as they are vector valued modular forms, there's modular invariant partition function Z, which is Chi0 absolute value square plus m times Chi1 square, and m indicates the degeneracy of these operators. And these characters, one can be expand, and the vacuum character is, because conformal weight is 0, Q series starts Q to the minus C over 24 with this integer coefficient, non-negative coefficient of Q series, and the Chi1 is given similar way. But the vacuum character starts with 1 because there is a unique vacuum, and other character studies arbitrary non-negative integers, which indicates the dimension of these characters. And especially when coefficient has no poles, there's only one weight 4 modular form, which is E4. So differential equation becomes very simple with one unknown parameter, and it's called the Kaneko-Jaeger equation, which was they used in 90s, about 10 years later than physicists. And then this coefficient is related to conformal weight, and the conformal weight is in this two character case related to central charge, and the dimension of there's a related Newton model with Lie group, and the dimension is again given in terms of Joule-Cox number H, and Joule-Cox number H is all related to each other. Now, Matsu and Buki-sen discovered this table where two character cases are taken, identify central charge, 2/5, 1, 2, 14/5, and so on. And the conformal weight, non-zero and non-vacuum conformal primary operator vacuum character and conformal weight. And then they identified all of this as a level 1 versus Newton model, except the first one is Lie-Yang theory. Now, there's one gap which is unknown, and now is identified as a level 1 E7.5 versus Newton model. E7.5 is not Lie algebra. It's something called intermediate Lie algebra, and I don't understand its detailed algebras. But its dimension is 190, and the Joule-Cox number turns out to be 24. Now, Svitanovich and Deligne studied this series of Lie groups independently. Svitanovich, he's a physicist. He did in 70s and Deligne in 90s for this series of exceptional groups. So this includes all exceptional groups. I think I missed it, F4. I'm sorry. Between D4 and E6, there's F4. And Deligne gave a uniform formula for dimension of these groups in terms of Joule-Cox numbers. And then Deligne gave also symmetric product of this adjoint representation, among which there's theta is the highest weight, highest root, and twice the highest root to fix one representation, and its representation is again given in terms of Joule-Cox number. And Cohen-Diemann extended this to 25 formulas, and Landsberg and Manuel gave a general formula for dimension of the k times arbitrary integer times it is highest weight, highest root. Now, exotic E7.5 is intermediate Lie algebra discovered independently Matsu and Buki and Sen, and Deligne, Cohen, and Diemann. Its dimension is 190, Joule-Cox number is 24, and it's not really Lie group, so one cannot say it's simple or semi-simple, but it acts like a simple Lie group, Lie algebras. And it fills the hole which was discovered by MMS, and the E7.5, again, I skipped the F4, so there's D4, F4, E6, E7, E7.5, and E8. And Joule-Cox number E7 is 18, and the E8 is 30, so 24 is just halfway between 18 and 24, 30, so that's why it calls E7.5. And also these theories have a very nice relation called the causal relations, discovered by Matsu and Buki-sen. And the best way to characterize this relation, which we'll use later again, is using the parameter nu, which is Joule-Cox number divided by 6, and then Lie-Yang theory, effective Lie-Yang theory, whose central charge is 2/5. So effective Lie-Yang theory is different from Lie-Yang theory in the sense you are exchanging vacuum character and the primary operator characters. So then central charge becomes 2/5, and the conformal weight becomes a minus, instead of -1/1/5, it becomes 1/5. And one can identify this as some sort of, again, it's not even intermediate Lie algebra, but one can identify this as some sort of Lie algebra-like structure it has, with the dimension of a group being 1 and dual Cox number is 3/2, which is fractional. Now with this series, we denoted as chi5 nu, and then causal relation is if you have a chi5, which is EA theory, Fitz-Newton's theory of EA level 1 theory, which has its only vacuum character, and there's no primary operator, it's a precise vacuum, and whose partition function is primary partition function is vacuum partition function is Klein J function to the 1/3 power. And then EA theory, if we model out by one of these theories corresponding to parameter nu, then we'll get a theory with parameter 1/nu. That's the causal relation. And if you look at this, so if I multiply this theory with that, then we should get the EA theory. So if you look at the central charge, their sum is 8, and the conformal weight of these primary operators is equal to 1. So if you look at the characters, then when you expand it, it starts with 1, q to the 1th power for product of characters for each non-vacuum primary operators. So let me now introduce magic square and triangle. So magic triangle start from study of division algebras, which we learned in high school or maybe in college days. So which is finite dimensional division algebra over real number. Division algebra is a generalization of real number and complex numbers. And we know there's Hamilton discovered in 19th century quaternions, which is almost like a real number and complex number, but it's associative but non-commutative. Then later on, a couple of people discovered octonions, and which is non-associative and non-commutative. And there are only 4 division algebras, finite dimensional division algebras, and which we know very well. Now, for some reason, mathematicians, sorry, I think it's the same thing, have been studying the projective plane specified by 2 division algebras. So division algebra with division algebras. And this projective space, for example, suppose we do it with real numbers, then real number projective plane is RP2, which is 2-dimensional object. And I'm not sure about this, again, wrong. Real number is complex number is a CP2, and that's complex projective space. And the quaternion will be HP2, and octonion will be OP2. Now, we know RP2 is S divided by G2, and it has symmetry group S of 3, or maybe smaller part of it. But as algebra, one could say A1. Now, CP2 has a symmetry group SU3 or A2. Now, this guy, HP2, turns out to be symmetry group C3 or USP6. One can imagine that's right, but we don't know. I mean, mathematicians have figured out this a long time ago. And OP2 has symmetry group F4. Now, magic square, which was discovered during 50s and 60s by Freudenthal-Tits and Wimbergs, is a symmetric. I'm just giving a physicist interpretation. Symmetry group of this projective plane, and this is the magic square. So as I say, R on R is A1, A2, C3, and F4. But octonion on octonion is E8. And this is called the magic square because we are doing division algebra. And then out of, because I guess from physics point of view, it's somewhat obvious, there should be some symmetry group. And this symmetry group is sort of Lie algebra. So Lie algebra appears out of the this division algebras, and you can see F4, E6, and E7, E8 appears. Now, Svitanovich studied this object in 70s, And he managed to extend this one to this triangle. So A1, A2, G2, D4, F4, E6, E7, E8. And you can see this is the same series Muki, Matsuo, Sen discovered, they include E7.5 and Liang. And then you can see triangle is incomplete. And then that's during 70s, but he's had some book from Princeton Press, which is updated in maybe 2000. But Deligne-Gross after Deligne series, they discovered, and because Deligne also figured out this series, then they filled this triangle. And they wrote down, but somewhat incomplete. It's not Lie groups, and they are not, and there's Liang, so there should be more, and it is incomplete. And recently, because we've been studying E7.5 and also this intermediate series, which is between E7 and E8 along this line. And then we somehow managed to discover all the element formally which fills all the gaps in the fill the gap in the magic triangle. So let me show what's the answer. Completion of magic triangle. So again, we start with this. First parameter is Landsberg-Manuel parameter, which is given in terms of dimension of these octonions, 8. I haven't talked about sextonions, and I guess I skipped sextonion is related to octonions, but you go to split octonion, which means 4 plus and 4 minus Lorentzian signature. Then you go to some sort of Lycon, then you can reduce the algebra to 6 dimension, which is not even division algebra, but it has some constant algebra in there. And the sextonion, some sense, generates some, let's say, I think some projective plane, then E symmetry group, one could say is E7.5, and so on. And then this dimension of the division algebra 6, 4, 2, 1, 0. Then 0 is D4, then this relates to G2. One can give some sort of, there's no division algebra, but I'm just saying there's a mirror kind of thing of negative dimensions. Now, related to that, there's a dual-Croxton number, and the dual-Croxton number is fixed. And I introduced the Deligne-Gross parameter, which is dual-Croxton number divided by 6, which is identical to 1 plus a over 2. And here's the parameter from 5, 4, 3, 2, 3 half, 1, 2, 3, 1 half, 1 third, 1 fourth, 1 fifth. So there's very nice reflection, inverse relation around 1, which is related to T4 best geometric model. And if I have 2 of T4, then I get a E8 best geometric model. So here is a extended version of the magic triangle and magic square. Then there's a magic triangle completed. And we look at some of these properties, and we realize that all these theories are built out of these atoms at this diagonal component. Firasol algebra 5.2, which is Liang theory, Firasol algebra 5.3, and U1 level 3, then Firasol 6.5, this is a three-state part model, and DA theory, which is reduced theory of the product of the Ising and tricritical Ising model. And then all these 5 theories, if I double them, I get the EA theories. And any of these theories, there are 30 theories, can be built out of these 5 theories. Right, so this if you look at these theories, there are 30 theories, out of which, and because there's a reflection invariance, so there's 30 theories, out of which 17 have standard Lie groups, and 13 of them has a strange intermediate Lie algebra, some of them, and some of them even we are not sure whether it's intermediate Lie algebras, but it has dimension and Joule-Coxeter number, at least from very naive sense of phase-generated models.
Can I have,
Right, so yeah.
have a question? In the previous slide,
Yeah.
actually the previous one, there are numbers on the triangle on the left.
Oh, here.
No, on the page before. No, not those numbers. They were like, one is the dimension. Yeah, here on the left. Each square
Yeah.
has two
Oh,
numbers.
right.
What's the
Oh,
interpretation? I guess one is the dimension and one is some representation.
minimal
Minimal
dimensional,
representation.
but it does make sense. E7 we know
Yeah.
56, but E7 133, E6 27. So I think he's representing some representation. So F4 52 52, F4 52 26.
So my question is about, do you have those numbers for your extended diagram?
Oh yeah,
And what's the physical interpretation?
Oh, so we don't have, because our case everything is symmetric, but we have the dimension which is straightforward to work out, and that's like because we have 4 characters, and we haven't really completed the whole things, but intermediate because of pretty everything is known, and also if you know the atoms, then you can build up all the numbers also. But those are representation of the series. So, for example, we'll see later, but it gives you the various dimension of the representation.
Okay.
Right. So here, this acts like there are 2 characters, right? T4, of course, T4 we can have 28 and 8, but turns out this series have 4 characters. So 1 vacuum and 3 independent characters. So we have this theory, then we fill all the theories, and I'll just talk not the detail of the rest of the series, especially we wrote the detail of the theory along this series, but I'll mainly talk about these 5 atoms and some general properties of this series. Right, so first general model, as a brief review, we have some Lie algebras or Lie groups, and then we have dimension and Joule-Coxeter number. Then we have 2D chiral algebra, which is one can build up from the first generated models. So where we can have a conformal field theory, then from mathematical perspective, VOAs with current algebras, and level K, and K goes from 1, 2, 3, 4, and so on. Then central charge is given by K times dimensional group divided by K plus Joule-Coxeter number. That's what we'll use mainly. Now we found uniform, dimension formula was known by mathematicians. And we applied to, we used this dimension formula to identify the gaps in this magic triangle. So dimension is given in terms of this parameter mu and nu, which runs from 1/5 to 5th and 1/5 to 5th, and their product has to be bigger than 1, so that you are in this side of the magic triangle. This side is like a dark side. There looks like there's something going on, which I'll make some comment later on, but we are not quite sure about. And so dimension is given, then we found Joule-Coxeter number is again given uniformly in terms of this parameter mu and nu. And then for level K equal to 1, central charge is now easy to write down because we have this formula. And this gives you a formula, a beautiful formula. And then we found, because we know some of series, more specifically, we can find general 4 primary operators, and their conformal weight is given in this form. So mu and nu, then I goes from 0, 1, 2, 3, and vacuum character, then there are 3 more characters. And Hilbert space of course, is made of for each primary operator plus a chiral descendant. Now, characters, which is torus partition function for each Hilbert space, is again we can expand in terms of, because it's a trace of Q to the L0 minus C over 24. So exponent is given in terms of minus C over 24 plus eigenvalue of L0, which is HI, plus the contribution from descendant. So this non-negative integer power, especially first coefficient, shouldn't be 0. And for vacuum character, we start with 1. Now, we note that this coefficient exponent has an interesting property, alpha 0 equals to minus alpha 1, and given in this form. And alpha 2 and alpha 3 is given in this form, and their sum is equal to 1. Especially, it is symmetric on the exchange of mu goes to 1 over mu, and u goes to 1 over nu, under which they are exchanged, but this one is alpha 0 and alpha 1 is exchanged. Now, central charge also goes to minus mu nu. So if you look at the Liang theory, effective Liang theory has central charge 2 over 5, but real Liang theory is central charge minus 22 over 5. So this reflection doesn't lead from effective Liang to Liang theories. Right, so this symmetry relates to this exponent in this manner. So dark side, which is mu dot nu smaller than 1, sounds like identical to light side, which is bright side is mu dot nu is bigger than 1, because this reflection exchanges two regions. So this part of a triangle is mu dot nu is smaller than 1, and maybe there's some way to give a meaning. Now, k equal to 1, l equal to 0 case, the characters satisfy fourth order modular linear differential equation because there are 4 characters, and the general case was studied by Setsu Sakai in 2018. And we find all the coefficients. This is the general equation, which is modular and no poles. So weight 4, weight 6, weight 8, they are unique. So that's the only 3 unknown coefficients. And these coefficients are given again in terms of mu and nu parameters. And this is invariant on the mu and nu going to 1 over mu and 1 over nu. Right. So especially one of parameter mu and nu equal to 5 is basically Matsuo-Muki-Sen or Sosanovic-Deligne series with 2 characters. And remember, we started with 4 characters. And turns out our quartic equation factorizes into product. So this 2 character has to satisfy second order equation, Kaneko-Jegi equations. But our quartic equation for this parameter factorizes. So again, these 2 characters satisfy Kaneko-Jegi equation. Then it satisfies our equation, quartic equation. Now, conformal field theory on these magic squares or VOAs has been named. This Freudenthal-Tits series and this intermediate exceptional series, which we identified and studied last year. And then sub-exceptional series, the Savory series, and Savory section series. I think this is just series in terms of Lie groups, not in terms of VOAs. And they discovered this series for some reasons. So as I said, there are 30 theories, out of which 17, you can count it, have a standard Lie algebras. So one of the things about these guys, like U1 level 3, A1 level 3, A2 level 2, this guy, or A1 level 8, this theory effectively has a different dual constant number. So if I go to level K, then from standard form is A1 level 3K, and this will be A1 level 8K, and A2 level 2K, and so on, and U1 level 3K, and so on. And rest of, we are studying level 1 theories, basically. And some of this guys are some sort of intermediate algebras. So there's some sort of group notations, and these guys, we are not sure. Even one can put some intermediate algebra kind of a name into it. And this diagram for dimension zero constant number, you can see this one is -1 zero constant number, two of them. So as I said, this is three-step palm model can be regarded as some sort of phase Witten model of dimension 0 and zero constant number -1, and this is a product of Ising model plus critical Ising model and the dimension 0 and the -1, and central charge and conformal weights, and the degeneracy is not complete. Now let's look at the magic courses and the 5 atoms. So in Shatanovich-Deligne series case, theory with 5-5 coordinate is E8 level 1 theory based simulated model. And then we find there, this is the MMS discovery that if we have level 1 theory, then if I divide by theory related to level 5 and nu, then we get a theory level 5 and 1 over nu. So for example, if I have E8, say D4, level 1 phase theory, then this is D4 level 1 theory. And if it's G2 level 1, this is F4 level 1, and so on. Now we discover that this can be generalized to arbitrary combinations. So suppose we have 2 theories, and suppose one of index is same rho, and that is mu and nu, and mu is bigger than nu, and then this theory, when you mod out, is equal to mu, theory mu, and 1 over nu coordinate. So that leads to a nice relation between characters, and with the coefficient x0, x0, 1, 2, 3, and y0, 1, 2, 3 being integers. Especially this causal relation, when we look at the specific characters, so this vacuum character and this first, second, third character with different conformal weights, and the dimensional representation being R1, R2, R3, then this previous relation, of course, leads to, from the leading terms, various relation between dimensions and dimensional representations. But one has to go through each series to look for this coefficient in detail. Especially we find this relation, CD series with intermediate series, then if any series along the line, we get a ratio is just given by effective Liang series. And if you divide, so let me go to, again, triangles. Okay, so let's go. So all these series and this series, so CD series and intermediate series. So I choose any one of them, divide by this guy, then I get this one. So if I multiply to any of these guys, this series, then I get this. So you can see atomic perspective. Say, theory multiply this guy, multiply this will be A1. If I multiply these two guys, then I get this. Then I multiply this to that, then I'm multiplying 3 of them, then I get A2 and so on. So that's the basically atomic structure and the quotient structures. So if I multiply these 2 guys, then I get M2. Then I multiply this to them, then I get A13. So this SU2 level 1 products, 3 times product, direct product. Right, so that's this relations, and that's force us to relation between dimensional representations and dimension of the generalized algebras. And especially one get very nice relation. So this tells these atoms, and depending on how you look at it, this will be double gap. So I needed 2 atoms product, which is A1 level 1, and it is a 3 gap. So I need 3 atoms to make a jump. So again, if I go back. So A1 times these series will be A2, G2, and so on. So if I divide by A2 divided by this guy, then I get A1. I get G2 divided by this guy, then I get A2, and so on, because right. Oh, sorry, I multiply this with that guy, then I HE2 because I have this guy is made of this object, and this made of this object, and G2 is made of this 4 object. So I can make a bigger ones, and then I make a small one, then together I have a big triangle, then F4 is made of A1 times C3, and so on. So we have very nice quotient relation between series, which wasn't known before. Right. So from this quotient relation, one can see that all 30 series on triangle at level 1 can be built from the series along the line, diagonal line, which is 5 series, which I said before. And so there are these 5 series. Here's coordinate, and there's also reflection to the diagonal reflection along the this way. Then you go to the other side. And this series dimension 1, 1, 1, 0, 0, and dual Coxton number is given by that, and -1, -1. So obviously, if I look at central charge, then central charge is dimension divided by k plus dual Coxton number, and the dimension is 0, and level 1 plus dual Coxton number, which is -1. So it's 0 divided by 0, because 0 divided by 1 minus 1. So central charge is not well defined. But because our formula is continuous, and we go through this central charge formula. So here's the dimension. I said that some cases dimension is equal to 0 because of this coefficient. But k plus 1, k plus dual Coxton number is equal to again 0. But because of this relation, we can go to any coordinate and then continuum, and we approach continuously. Then those 0 divided by 0 makes perfect sense, and it gives you a regular central charge. So these two series with dimension 0 and dual Coxton number -1 have different central charge, 4/5 and 6/5. And 4/5, as I said, this is a tri-state part model, and this state with primary operators and degeneracies. And your U1 level 3, again, central charge is 1, but U1 theory has a dual Coxton number 0, and central charge is 1, dimension is 1, and here's degeneracy of state, primary operators. And this two series, and Liang theory has only 2 characters, so H1 disappears, and H3 disappears, and H2 is meaningful. And then D2A is basically product of that, and you reduce the VOAs or operators, then this series central dimension 0, dual Coxton number -1, central charge is 6/5, and here is the degeneracy. So with this series, we can build all the 6 series, and we know there's S-matrix, and from there we can build all the S-matrix over 30 series and so on. Right. So as I said, major concept. So G2 is made of this 4 series, and F4 is made of this 5 series, and then you can see it all together, or 6 series. Then you all together, they make a E8. So G2 times F4 theories, I mean VOAs or conformal field series. When you make a direct product, we get a E8 series, or I can divide by, then we get a, say, F4, E8 divided by F4, we get a G2. Now, this case, we have a D2A appearing twice. In this case, if I make a C3.5 with D4, then I have to divide the double appearance of D2A. So we make a product divided by D2A, then we get a E7.5. So that will be more generalization of magic quotient relations. Now, in this case, we have 3 bits of a series product, there are 3 series combined into A2 and 2 series combined to M2, and then this series combined into D3.5. Then all together they combine to E7.5. So that will be another relations. And then as we play around, we found there's one more very interesting relation, which is called magic quadratic relation or quadratic relation. So as I said before, alpha 0 is minus alpha 1, which is alpha I is the exponent of characters leading term q to the alpha I times q series with integer coefficient and integer powers. But this primary operator, vacuum operator, and this first primary operator exponent has opposite sign. Now, second and third one, exponent is given in this form, and their sum equal to 1. Especially if you look at this one of elements, which is 5-3 element, so that's this element. If you look at this, this effective Virasoro algebra of 5-3, and which has central charge 3/5, but real Virasoro algebra, of course, this series is non-unitary, has central charge minus 3/5. So you could imagine if I make a product of these two series, I get a central charge 1. Only possibility is just some constant. And we can show that indeed, if we look at the character formulas, vacuum characters and the primary operators, they change their place. Alpha 0 and alpha 1 change their place. That's how central charge changes from minus 3/5 to 3/5. In this case, characters satisfy vacuum characters of this theory, vacuum character and the first primary operator character minus second primary characters for second and third operators is equal to 1. So in some sense, you make two series and direct product, and the central charge is equal to 1 and 0, so series should be trivial, which is identity. Now we found, except Deligne series or Saturn Deligne series, except at the bottom and this vertical series, we are still trying to understand what's going on. We found characters have this beautiful relation, chi0 times chi1 minus chi2 times chi3, is equal to generalizing these formulas. It's constant, and turns out to be it doesn't necessarily 1. It's related to R1, which is coefficient or leading coefficient of chi1, which is dimensional representation of a chi1 primary operator. With these relations, we find a relation between 3 primary operator dimensions, R1, R2, R3. This is R1. This ratio is again given uniformly in terms of mu and u function. And this again beautiful. And remember, we had a more relation between dimensions from this quotient relations. There is an additional relation like that between various different representations. But the relation we write down is for given mu and nu, they satisfy this relation. So, and also, of course, 5 atoms generate all the series. So it will fix the old coefficient R1 and R2 and R3. R1, R2, and R3, but it will be interesting to find out what those are. In many cases, we know what's going on. So that's for level 1. So now let's look at the higher level best generator model for this 30 series. Now for 2 atoms, this 3-state PAM model and the product of Ising and tri-critical Ising models, their dimension is 0 and zero Cox number is -1. Now, when level is 1, it's 0 divided by 1 minus 1, so one can have a non-trivial central charge. But if level is 2, then 2 times 0 divided by 2 minus 1, so central charge is equal to 0. So all higher level theory will be trivial. So for this series, but all the rest 28 series, if you look at it, then the Joule-Cox number is not -1 and dimension is non-zero. So one can, in principle, define the higher level series, especially if they are best Jumno-Ito models, or even some atomic theories, like these guys don't have clear sense of the intermediate Lie algebras. Still, these three, I mean, Yuan theory, of course, we know it should be well defined. All three of them has arbitrary higher level models. And also, we studied quite a bit of the other sub-series of these triangles. And in this time, we noticed that especially sub-exceptional series, level 2 sub-exceptional series. So level 1 is U1 level 3, A1 level 3, A1 level 1 to the cubic, C3 level 1, and now it's a level 3 series. So then level 2 series, and this level multiply 3 to 6, 3 to 6, and 1 to 2, and so on. And for this series, there is something remarkable. All these series can be fermionizeable, which means this theory has either dimension 1/2 or 3/2, and also they are all supersymmetric. And their central charge is uniformly given in terms of the A variable related to this. So mu and nu, and say mu is like a 3, and nu can be changed, and in terms of A variables, central charge is given in this form. And now total number of characters a lot, and in fermionic forms we have 4 ns characters and 5 RNS characters, and the NS or NSR is same, and here is the primary operators with vacuum characters and 3 non-trivial operators. Now, RNS characters, you can see 4 non-trivial plus 1 constant. Constant means this is RR character in some sense. And the RR character is 1, which means RR Witten index basically is equal to 1. So supersymmetry is preserved. And then this will be RNS characters and RR characters. And so not only, but there is no uniform relation between causes except a series that we found. So this again, Shatranvik Deligne series level 2, and the sub-exceptional series level 2 times A1 level 2 is basically a Virasoro algebra with PQ n plus 1 and n, and the n is given in terms of these parameters depending on parameter a's. Now, again, subseries divided by Savary case, again, one can give a uniform formula, and this is the Bosonization of the n equal 1 minimal models with these levels. So to conclude, we complete the magic square, and the characters of level 1 satisfy fourth order modular linear differential equation. And we find the magic relation, which generalizes the dual pair with respect to E8 in Shatranvik Deligne series. And this causal relation for this series has been discovered by MMS to whole magic triangles, and from which we find 5 fundamental objects, which we call atoms. And that gave us more generalized, it lists all the construction of the 30 series, and also it led to a very interesting quadratic relation between characters in given theory. And also we find a uniform concept construction for level 2 VOAs. Now, okay, this could be a bit academic, but recently E7.5 appeared as physics related to 4D n equal 2 superconformal field series by Hyun Kim and Jeon Song. And we hope that all of this 30 theory may have some relevance too, especially in non-unitary theories, because this series are related to non-unitary theories, will be related to some of 4D n equal to conformal field series. Thank you.
Okay, let's thank Kimyeong. And Van, you look ready for a question.
I already asked one.
Ah, okay. No, just because you suddenly appeared. Good. Do we have questions?
Hi, Kimyeong. Actually, I have a question. Hi, Kimyeong. Yeah.
Yeah.
So I'm wondering, like, for those like intermediate algebras, do you have like a num-sum type expressions? Because like I guess in Hyong and J1 they have some like like a when they compute those
Right.
characters, they have a special form. So
We haven't tried. I think minimal models have num-sums. So some sense,
yeah,
if you have U1 level 3 has num-sum, then maybe because of atomic construction, maybe all of them has num-sums. But
so maybe
I'm
then we
not sure.
can try to guess what could be the like a
Right.
higher dimensional. Yeah,
Yeah, indeed. So then we can go to 3D. Maybe that would allow us to go to 4Ds and so on. Yeah, so
I see.
then, and
Yeah. I see. Okay, thank you.
And so
also there's
Hmm?
stories related to generalized symmetries, but I haven't. I'm thinking about, but I haven't done it.
So out of the new, or I don't know if new is correct, but the algebras that you find, they're not, simple Lie algebras.
Right.
Like for example, a E7.5, of course, this is by now like, let's say, almost well known. But the others, do they appear in some math context? Like could you find them in some other places?
Oh, so I was talking to some of a representation theory guy in BIMSA,
Uh-huh.
and they find E7.5
Yeah.
and many others. So I
Mhm.
suspect they may find all of them from some
Mhm, mhm.
representation theory perspective,
Like,
which is completely different angle.
because it would be nice to, like, if there is some property that these Lie algebras have that make them, like, they're not simple, but still they're in some special class of Lie algebras in, the huge space of Lie algebras,
Right.
that there's somehow, there is some appear here, but I see.
What is this completely different context in which they find them?
Oh, I was talking to him. They are looking at some, I don't know, they are pure mathematicians. And they are looking at some strange algebras, nothing to do with anything we are talking about. And they see something odd, then they can see some of them are related to E7.5. So maybe maybe I'll talk to some of these guys, and then as soon as my paper is finished, then I'll show them and then talk. So from their context, they said that there are a lot more than just E7.5. So maybe all of these guys up here, I suspect, in some way. Now, there's a D2A. The reason D2A is because it's related to monster groups. So monster group has no linear algebra because it starts from 1 plus Q square. And you can divide the monster with either D2A or this tri-state palm model. If we divide by this, then we get a Fisher 24. D2A, we get something. So one can imagine something similar to generalized theory for M monster group instead of E8. Then all of this guy will have no yuan dimension will be zero because E8 monster has no yuan symmetry. And then you have to build up something along not the magic triangle. So one of it is the E8 extended thinking diagram or McKay correspondence, which gives some elementary object plus some of the like Ising model plus baby monster generate E8. So there's some series of this type of relation, much bigger, much broader than this simple magic triangle. But
Do we have more questions? Okay, then I would say let's thank Kimyeong again,
All right, thank you.
and we can go off the record.